What Nicole and I are going to try to do is sort of frame an argument that cities can be carbon sinks instead of emitters, like forests, and in fact work economically and ecologically in synergy with forests to store carbon. And that's basically our argument. So it's a kind of economic one. And that's what we'd like to talk about today, essentially monetizing carbon. Now, we're not economists, so we won't get into deep economic theory, but really it's an issue of exchange. It's an issue of a material exchange between forests and cities. Everybody knows about carbon. Carbon is an incredibly ubiquitous element in our world. Carbon forms polymers at an astounding array of polymers at Earth's terrestrial temperatures and pressures. One of the most important ones, of course, is CO2 because it's accumulating in our atmosphere. Before the Industrial Revolution, we had a fair amount of carbon in the atmosphere. It's part of the normal carbon cycle. And we had an enormous number of carbon sinks that exist terrestrially. The atmosphere, oceans, the biosphere, forests largely, the aquatic biosphere, of course, fossil fuel reserves, hydrocarbons in the lithosphere, kerogens, which are organic compounds that have fossilized. Before the Industrial Revolution, there were about 278 parts per million of carbon in the atmosphere. Today, we're at 408 parts per million in the atmosphere. By 2050, we're looking at over 500 parts per million in the atmosphere, which is unsustainable, of course. That's actually a record of the kinds of carbon measurements that have occurred since the Industrial Revolution. At 2015, we skyrocketed past sustainable levels. And it corresponds largely with anticipated population growth. We'd like to separate population growth, which is inevitable, from this kind of charging, accelerating climate change due to carbon concentrations. So nearly 10 billion people by 2050 will inevitably be emitting through their consumption of products largely, and consumption of energy. They'll be emitting a significant amount of carbon. So how do we separate those two trends? There's our benchmark, which gets us to about the anticipated 2 degrees Celsius temperature rise that we're trying to avoid. It happens at about 2035 at current business as usual. We have a carbon budget of this much. I'm looking over my shoulder, so I'm having a little trouble with this. We have 617 billion metric tons of carbon that we've consumed, which seems to leave a lot for us to consume, but that'll only take us 18 years at current levels of consumption and emissions. So we know the industrial sector is a big consumer of energy and emissions of carbon dioxide. 28% goes to transportation. And between production and operation, the building sector consumes half of that budget. So we have a big stake in this, in our profession and in our building culture. I want to talk a little bit about embodied versus operational energy very quickly and put it into a time scale that Peter's already sort of addressed. The buildings that we build today will produce an enormous carbon spike. That carbon spike basically is us loading all of the production emissions of a building right at the outset of the life cycle. Our operational emissions start at 0 and they increase slowly over time. And they actually intersect or pay off our carbon spike from building production 17 years out at about 2035. That's about the time that we're going to cross over that 2 degrees Celsius temperature rise. So it becomes pretty important to think about embodied emissions because we won't pay it off until, even with our most efficient buildings, we won't be paying it off for quite a long time, perhaps when it's too late. These are our emissions annually. This is how much global steel we consume just in the building sector. This is how much cement we consume. Half of the energy goes into buildings. Half of the wood goes into buildings. All those in ecosystem services, half of it go to and forests go to building, and we produce 65% of the waste. At the rate at which population is growing and urbanizing, if we keep building using the same spatial morphologies we build with, we will consume 3 times the land area that we currently have for cities building. So how do we answer this? President Trump's administration has just announced that they're going to invest in carbon capture, and what does that mean exactly? What are the carbon capture and storage systems that are being proposed typically? Basically, what we're using is the same technologies that we use to produce hydrocarbon energy to sink carbon into the back into the lithosphere. This is kind of what it looks like technologically. It's pretty familiar looking. Essentially, what we're doing is taking these lithospheric reserves of fossil hydrocarbon, we're drawing that energy out of the earth, and we're trying to take the carbon we emit in combusting that fossil hydrocarbon, and we're basically trying to pump it back into the lithosphere. My slide advance is no longer working. And so there's a technological cost to that. And even if we use, bioenergy, carbon capture and storage systems, we're still paying a lot of money, $250 per metric ton to sequester that carbon. And we're actually incentivizing the growth of plantation forests or other kinds of forms of biomass to be able to meet those demands. So the numbers aren't really working that well. So this brings us to a question of technology. And the definition of technology is quite simply the methods, materials, and devices that solve our practical problems. But if you take it a little further, it's really a relationship between that technology and problem-solving artifacts that we create and the means to solve them. And the final definition, which I like so much, is the way in which technology itself determines our practical problems. And so in some senses, carbon capture and storage technologies that the Trump administration and the fossil hydrocarbon industry is talking about is really a sort of new artifact that we will have to solve. So the question is, can this particular carbon capture and storage device, the forest biome, actually become a technology?
Can you hear me if I have this on? No. Is this working? I should say I'm Nicole St. Clair Knobloch, and I'm here. I am a fellow at Harvard, but I'm really here as the head of the Build It with Wood program at the New England Forestry Foundation, where we're working on creating a nice regional forest to urban carbon sink. So what Alan has just, sorry?
I think I jumped. I haven't done this yet.
Okay, so Alan is just going to talk a little bit more about the carbon capture and storage technology that is our forest biome, and then I'll start talking about how we want to value that.
Yeah, sorry everybody, I jumped.
Okay.
I was so excited to have Nicole talk that I got ahead of myself. So just quickly to look at the forests. Everybody knows about photosynthesis. We've talked about that a great deal. The photosynthetic production of carbohydrate and consumption of CO2 or uptake of CO2 is a pretty fast cycle. It operates at between 40 and 100 years, roughly, 150 for certain kinds of forests. The fossil industry is quite fond of talking about the fact that fossil hydrocarbons are also renewable, but the time frame in which that happens is a little different, and obviously it's absolutely meaningless for us at this point. If we think about the way we build as builders, and again, I'm an architect and a builder, the idea of the forest as a source of material has been something that's been a very durable part of our culture. But as we've advanced technologically, we started to dig deeper and deeper into the lithosphere to kind of extract not only material for purer and purer homogeneous systems that we can develop technologically, but also energy systems that sort of fuel those manufacturing processes. And what's really important to remember is that along with this comes an enormous emissions of CO2. So we're very fond of comparing the emissions of different material classes. We talk about concrete as having a certain kind of emissions footprint as being very large. What's really important to remember is what you get for that emissions. The strength to weight ratio of timber means that the relatively comparative emissions of cement production and wood production per ton gives you a very different result, which is, let's think of it as a strength to spanning, emissions to spanning capacity. If you add sequestration into that, you get huge benefits, and that's what we're going to try to talk about today. This is your net forest carbon transferred into wood. We get a benefit of half a metric ton of carbon dioxide sequestered, even though we spent emissions to produce the wood. And this is the difference between harvest and deforestation. Harvest leaves that soil biome intact. Deforestation strips it entirely. This is deforestation, and one of the drivers is mining. And then we have the accumulation problem, which is when you take all that material out of the ground, where do we put it and what does it do? So these are the drivers of forest cover loss or forest conversion. Agricultural conversion we talked about, mining, suburbanization, and of course climate change itself can cause forest cover loss. So lastly, what I want to talk about is density. Why does density matter? We have a lot of skills in the forest industry. We've built our country out of wood, but what we've built largely out of wood is this spatial morphology. So why is it that the most intensive extractive methods produce the most efficient morphologies in terms of land use? And why is it that this relatively more efficient material system produces the morphologies that are actually land intensive, infrastructure intensive? I mean, look at the comparative use of wood and its carbon footprint for buildings of different scales, the suburban versus the urban. And then if you expand that to the landscape of the suburban landscape or the urban landscape, you start to see that the city has enormous potential as a carbon sink. So how do we take those two landscapes and how do we redistribute wood fiber to make it really effective as a carbon sink? And so what Nicole and I are going to talk about is a sort of regional regenerative city supply chain, which links two landscapes. We typically link the extractive landscape to the city and the harvest landscape to the suburb. So we want to break that relationship and we want to link it through regional forest supply. This is where I turn it over.
I thought that went so quick. So the whole first part of this presentation shows us what business as usual, conventional materials, steel and concrete are costing us in terms of emissions and blowing out our carbon budget in the next 18 years. And also showing us basically that obviously mass timber is a solution that can come online to reduce those emissions, avoid those emissions, and sequester carbon. But then that brings us to the question of, well, how do we value that service? How do we put a value to the carbon being sequestered and the emissions being avoided? And how do we devalue the carbon intensity of conventional building materials? And until you do that economically, you don't get the projects, as we all know. So I think what I want to go through now is just there are two major policy regimes that are out there now being used for the other fossil fuel intensive sector, which is electricity. And so that's the input to our buildings and to our manufacturing that relies quite a bit on fossil fuels. So the first and in a way simplest policy regime is the carbon tax, even though it's not necessarily the most effective and may not spread through society as quickly as some other ones. But I'm going to explain it, which is basically you have an entity like an electric utility and you charge for the carbon that they're responsible for. And the idea is that the more expensive it is to use a fuel like coal, the more that utility is going to be incentivized to switch to something cleaner. The carbon tax is simple in that you just price the carbon, the entity pays, it goes into government coffers, then you decide to do with that money. Now it can seem sometimes like that can be a real revenue source for clean solutions. Sometimes carbon taxes are set up that way where the tax itself, those revenues are cycled back into cleaner energy alternatives. But more often, because there's such political opposition to new taxes, those regimes in reality, in real life, end up being what's called revenue neutral, where they just bring it back and reduce the sales tax or reduce some other tax, a property tax, so that the entity being taxed feels the pain of the tax, but it doesn't translate into what might be perceived as a new tax. So I think the more interesting and perhaps fruitful regime for our purposes is cap and trade. And I don't know how many of you have even heard of cap and trade. Have any of you heard of cap and trade? Oh, good. So I will explain it, but it won't be brand new. So cap and trade is where you get a whole marketplace of entities that are polluting and that are striving to drive their emissions down. And you put a price on those emissions, and you turn it into a credit if you're if you're an entity that is, weaning itself off of fossil fuel and making investments in both directions, in new sources like wind energy and in greater efficiencies, then you can end up being given credits for those pollution reductions. If you have a certain amount of pollution that you still need to emit because you're driving your carbon down over time, but you haven't yet made those investments in wind, or something else, and they haven't yet come online, then you have to purchase the right to pollute, which is called an allowance. And so that becomes, this is actually a nice little sort of abstract illustration of the two entities. So the one you have on the left is the utility that used to really run on coal, and now it's, half of its operations is they're getting wind from the Dakotas, and they're really getting their customers to save on energy. The one on the right is based in Ohio. They're still quite dependent on coal. Maybe they're transitioning to natural gas, and they're sort of doing a slower transition. So those guys are going to have to, basically the guys on the left have something to sell, and the guys on the right have something they have to buy. And so then what you've really done is you've started to put that value on the cleaner alternative, and you've started to put a price on the continuing to pollute. So what you see there is, I'm trying to show the transfer here. But the other cool thing for our purposes is that how does the price on carbon get determined in a cap and trade? It's not like a tax where the state legislature says, okay, it's going to be $20 a ton to pollute, and that's what you have to pay. This is a marketplace solution. It's what the market is willing to pay for a permission to pollute. And so every year in the actual cap and trades that exist, and I'll talk about those in a second, there is an auction for these permits. And the companies all go and bid, and eventually the price is set basically by what the marketplace will bear to pay to pollute. And those auctions generate billions of dollars of revenue in the states where they're conducted. Now, so the little drop down we have from the money there is not totally a closed cycle, because there's all this revenue coming into the states where the auctions are held, and that is being sent down into the economy, into the marketplace, toward very specific types of projects to continue to reduce carbon pollution. So like energy efficiency projects, new clean energy projects, interesting building projects, which I'll get to in a minute. And that's where I think there's some real opportunity for mass timber to start to present itself as a major climate solution. And so let's see what do we have here. So cap and trade, we've got two big regimes in North America, really. The first is in the U.S., the Regional Greenhouse Gas Initiative, which is the northeastern states plus a couple of the mid-Atlantic states, Maryland and Delaware. It's now 10 states, or it's going to be 10 states again this year. It's 9 states. Chris Christie took New Jersey out of it, but then they put them back in because, as I said, it really generates quite a lot of revenue for these states, which they can use toward other things. And just as an example, $1.7 billion invested in 2015 from the RGGI allowances. Then we've got California, which I'm sure, as you've heard, is a huge leader on climate change and on reducing emissions. And so they set up the first cap and trade under the California Air Resources Board, which is known as CARB, the all-powerful CARB. And they have invited and managed to attract Quebec and Ontario to engage in that trading. And the nice thing about that is the bigger the market gets, the more activity that can go on, the more revenue that's generated, and the more innovation and drive toward new solutions. So we want to see those expanding. And then carbon tax, we've got fewer regimes of those, a couple in Canada and in Mexico, sorry. But as I said, I know that the 2 in Canada are, as I say, revenue neutral, meaning that there's not a lot of money cycling back to clean energy projects. So it's not necessarily at the moment a source of revenue, but could be. And then the other thing that's happening, which is very exciting, is you're starting to see, there was a real effort about 10 years ago for a federal cap and trade to just do this across the whole country, and it failed. We were kind of right in the middle of the recession hitting, the Affordable Care Act being enacted, and there just wasn't the appetite, I think, in the end to pass one more big idea. So, but in the wake of that, and even before that, U.S. states and cities have been recognizing the need to bend down the carbon curve for a long time, and they've been enacting a lot of their own policies. So we're seeing things, again, on the electricity side, like what's called renewable portfolio standards, where you mandate that like 20% of your electricity has to come from clean sources. But then we're also starting to see cities and states get really creative. And when the US decided to pull out of the Paris Agreement, which would have committed voluntarily to reduce our emissions 80% by 2050, a whole number of cities, I think 401 cities, committed to do their own version of that. And cities themselves are responsible for over half of our emissions, so it's significant for cities to do this. And it's kind of exciting when you read through what all the cities have done, and you look at major cities like Atlanta, Houston, Dallas, Chicago, LA, Boston. They've all set some version of that 80 by 50 target, and then they've all laid out ways to get there, including they've started just even measuring what their city emissions are. They're doing everything from switching out the streetlights to become LED, to putting in major new transportation systems, to doing a lot of energy efficiency initiatives. But what's interesting about that is they all describe buildings, the built environment, as being their #1 source of emissions, and a lot of them call the building environment the #1 end user. And this is our entree, is to start thinking about how do you get cities who are already focused on the building sector, who are already devoting resources to reducing those emissions, who don't need to be convinced that climate change is happening and that they need to do something about it. How do you get some of that revenue directed toward the actual materials that go into the buildings, and not starting out with that carbon debt that Alan has described that those buildings come with, but starting out with sequestration, avoiding those emissions altogether, and really starting to almost have like a city savings bank of carbon emissions. And does that go back to you then? And then that gets us back to connecting the cities to thinking about the forest cover around them, which currently cities are not thinking about or being responsible for, and we're kind of quietly losing, and which Alan's going to tell us about now.
Well, I mean, I think what's important to understand is the capacity of the American forest sink. I mean, it's enormous. It was 50% before 1500. We've lost a fair amount of land coverage, of forest cover. We're back down to 33%. It has the capacity to sequester it sequesters 11% of the carbon that we emit. It could sequester 30% of the carbon we emit. And so that brings us to this sort of biomass scenario, building biomass and structural biomass as a way to kind of help solve this problem that we face. We build with a lot of different species. We can build sustainably with them. Each one has a particular kind of template for a set of properties and means of processing and conditioning the wood, drying, preparing. They're harvested at different times for optimal mass of wood, but they could be harvested for optimum carbon sequestration. And then as we start to think about how we transfer those materials through this array of mass timber products and timber products into the building, this can actually be a way of thinking about life cycle carbon assessment, material flow analysis that, as Peter mentioned, should be part of design. If we look at the forest and we think about how forests grow and how that could relate to building and how we might manage forests sustainably in order to make sustainably managed built environments, we have to think about the different stages of successions that happen as we regrow forests after a harvest and what that does in terms of protecting habitats or creating new habitats. We took a piece of New England forest, 1,500 acres, and we analyzed how much carbon existed in it. Carbon stored in the stands that are harvested, carbon that's preserved in the area of the forest that you leave intact that you don't harvest, carbon stored in the soils. That's 50% of the forest carbon that exists in the New England biome exists actually in its forest soils. And then we start to compare this sort of exchange of material from the forest to the city, and we ran a model to really study what would happen if we clear-cut small areas, patch clear-cut areas, and started to transfer material from the forest into the city. So we took a section of New Haven, Connecticut, where there's an anticipated demand for building, a certain FAR, and we basically started to study what would happen to a 1,500-acre section of forest as we built a 2-acre section of the city. And over the course of 45 years, you answer the demand that's anticipated due to the vision plan for the city and the anticipated population growth in the city, and you also basically sustainably manage this section of forest. And in the end, we have a sort of carbon account in the city and in the forest. We have CO2 preserved in the forest. We have 51,000 tons reabsorbed through photosynthetic uptake, 34,000 tons sequestered back into the city. That's our savings bank instead of allowing that to rot on the forest floor and off gas, actually. And then what we've avoided by substituting wood for mineral-based carbon systems. So we have this carbon bank in 2 acres, 282,000 tons of CO2. We have the equivalent of nearly 64,000 vehicle emissions, annual emissions, stored there in this carbon bank. And if you monetize that at the current rate value of carbon, that's $8.5 million. And so what small city strapped for cash wouldn't like to get into a carbon market using just the buildings that it's going to build anyway as a means of creating an offset? So just to really summarize, we have this synergistic relationship. We want to try to measure it as carefully as possible, and this is where the building industry and the design professions can be really effective, because if we can measure it, we can manage it. The reason we would do this is because that we have a set of changing norms that are changing rapidly because of the conditions we face, and this presents enormous business opportunity and potentials for green funding. And the mass timber industry and the design professions should be tapping into these very powerful constituencies and sources of funding. And so if we want to really study this cycle of how forest grows, and we understand that there's this repetitive cyclical absorption and desorption of carbon from the forests, if instead in that lower graph we actually start to store that and we transfer it through cities and through building materials into cities, we know that we can get a certain kind of carbon benefit along the baseline by building, as we do now, mostly suburbia. But if we were to actually turn that into mass timber systems to build cities, we start to really game the carbon accounting that is such a powerful tool for us. And if we project that globally, and we imagine that we were to build all of the demand for housing across the planet for the next 35 to 40 years, we actually see a really surprising result, which is that this is business as usual. We're about to sort of run over our carbon account by 2050. At 2035, we hit that 2 degrees Celsius rise and that assumption, the sort of correlation with carbon emissions. If we were to build all of that housing out of mass timber, we start to bend that curve down. This is our savings. This is what we save in terms of carbon by sinking it in cities. And that bends this biomass projection, bends that carbon increase down below that 2 degrees Celsius temperature rise. Now, this is obviously a huge extrapolation, but what we're saying is that if we can really refocus, as Peter's already said and Nicole's suggesting, the way we think about embodied emissions and the way our material classes compete for carbon as a sort of monetized entity, we can really take huge advantage of this opportunity.